Hello students, welcome back to discrete mathematical structure classes, video classes. Okay, so in the last class we have seen open statement, existential quantifier, then universal quantifier, okay, then definition and facts. Today we will see this only few of these definitions we have seen, that is existential quantifier and universal quantifier. Okay, so we'll see this table. So in table what we are going to have, we are having a four statements. One is for sum of x p of x, and for all x p of x, then for sum of x negation of p of x, and for all x negation of p of x. Okay, so all these we are going to have. Now these are when they are going to be true or when it is going to be false. These things we are going to see. So when it is true, here it is. When it is false, that one we are going to have here. So there for some x p of x is true. For some means at least one a in the universe is true, then only it is going to be true. Means at least one element must and should be true, then only I can say for some x p of x is true. And when it is false, for every a in the universe p of a is false. If I say like this, if the word for every a or any a, if it comes here, I'll be having one more option, any. For any a in the universe, that time also it is going to be false. Next, for all x p of x, for every replacement of a from the universe, p of a is true. Here instead of x, what I have taken here is a. Means x means an free variable. I can take any of the element. A means I am specifying with respect to one element. Here also I am specifying with the one element. For every replacement of a from the universe, p of a is true. And there is at least one replacement of a from the universe for which p of a is false. If we one for at least one a, if it is false, it's going not the given statement is not going to be true. Okay, similarly with the respect to this negation of the same p of x, if what we are going to have for some x sorry for some x, negation of p of x is true. If it is true means there must and should be at least one x value such that negation of p of x is going to be true. Means for at least one choice a in the universe, p of a is false, then its negation of p of a is true. Do not get confused here. P of a is what? It must should be false, then only it is true, because in the statement we are going to have a negation. If negation is there means that should be false, then I can say it is true. Okay, similarly for every replacement a in the universe, p of a is true. Okay, similarly for all x, negation of p of x. Now here what I am going to do, for all the value I am going to replace with the some a. Okay, that time it should give me false value only, then only I can say it is going to be true for all the replacement of x, otherwise it is going to be false. Next we are having, there is at least one replacement of a inverse in the universe which negation of p of a is false, and p of one must be true and another must be true false, then only I can say is it's going to be false. This is one table. Next we'll go with the one more definition. So in definition we are going to deal with the one is logically implication, which also equivalent to logically implies. Okay, so for this we are going to see here. We have learned these two things with respect to primitive statements. Now with not only with primitive statements but along with the quantifier also we are going to see. What is the definition? Let p of x and q of x be open statement. So these two are open statement. Okay, so that is with defined with respect to particular universe. Once it is done, the open statements p of x and q of x are called logically equivalent. Okay, these are logically equivalent. If they are logically equivalent, I am going to use this particular symbol. Okay, so if we write for all x, if we write for all x p of x, is logically equivalent to Q of X when the biconditional P of A is logically equivalent to Q of A is true. For each replacement, we should remember here for each replacement, because we have used is for all X. Since there is a for all X, we must and should have here is for each replacement of A from the universe. That is P of A is logically equivalent to Q of A for each A in the universe. When it is true, I can use that one with respect to implication. If the implication P of A implies Q of A is true for each in the universe, then that is P of A is logically implies to Q of A for each A in the universe. We can write that time. See here, when I can say is logically implies when it is biconditional value is same, also it should be logically equivalent, then only we can tell it is going to be logically implies. When this particular statement, okay, just a minute. For any of the p value, this particular a, what the value I have changed here, okay. So here also, here it is for p of a is logically equivalent, means what I can say, it is also p of a is logically equivalent to q of a. Another word I can write is q of a is logically equivalent to p of a. Okay, so this is also going to be true. If both are true, then only I can say is P of A is logically equivalent to Q of A, or else we can say P of A logically implies Q of A. Okay, so what we can say at the last, we can say is for all x, P of x is logically implies Q of x, then only it is going to be true. This is one definition. Understood? Okay. It has been given example. I'll just rub these things. Okay. So now what we are going to have? We are having a one example. Let us see the example. So for the universe, all the triangle in the plane, let P of x, Q of x denote a open statement. Okay, so x is equiangular and x is equilateral. So both are going to have P of x is equiangular and Q of x is equilateral. So now when it is equiangular, it can be equilateral also. When it is equilateral, it is going to be equiangular also. Okay, so when it is a condition, what we are going to say, then for every particular triangle A, that is replacement P of A is biconditional with the Q of A is true. Okay, so consequently for all x, P of x is logically equivalent to Q of x. Okay, so now what I can say, observe that from the definition I can write here is for all x, P of x logically equivalent to q of x if and only if for all x, P of x logically implies q of x. Like this also I can write, or else I can also write for all x, Q of x logically implies P of x. So both are going to be valid one. Okay, next one more definition we are having over here. So for all the for open statements, P of x and Q of x defined for the prescribed universe and the universally quantified statement for all x, P of x implies Q of x, we define contrapositive, converse and inverse. These we have learned with respect to primitive statements. Now we'll see with the same thing with respect to quantifier. For all x, P of x implies Q of x. To be for all x, negation of x implies negation of P of x. What is the changes we are having? We are having for all x, then we have inside x, this is also x we are having, here also x, here also x, and this for rest all remains same, and here also converts for all x. But remember one thing, we are not defining this one with respect to existential quantifier, but instead we are defining that one with the for all x. Okay, so this is going to be valid, not a this one. So only whenever it is for all, that time we can use all these three laws. Okay, next we are going to have few more logical equivalence and logical implication quantified statements in a one variable. uh, Here, for a prescribed universe and any open statement p of x q of x in the variable x, for sum of x p of x and q of x logically implies, then if I write that one, what it will give me? For sum of x p of x and for sum of x q of x, right? Then sum of x p of x or q of x is there, I can split those things and I can write over here separately. Then for all x p of x and q of x logical equivalent to for all x p of x and for all x q of x. Okay. Next one we are having for all x p of x or for all x q of x. Separately for x or x, it has been written, since here also it is x and here also it is x and here also for all x and here also for all x, and I can write here is commonly for all x inside what the values we are having, p of x and or q of x. So here it is p of x or q of x, that one we have written. If suppose it is for all x and here it is for some x, that time I cannot write this one. Following? Okay. And here it is one more example, that is rules for negating a statements with a one quantifier. Negation of for all x p of x is logically equivalent to, if I apply negation to for all x, it will become for sum of x, and p of x open statement will become negation of p of x. Similarly, for sum of x, p of x will become for all x and p of x will become a negation of p of x. Now we'll have a apply negation to here. Negation of for all x will become sum of x. Double negation of p of x it will become, and double negation of p of x will be using a rule of double negation. Double negation will get cancelled, so I'll retain with the sum of x, that is p of x. Similarly for this one, for sum of x, negation of p of x, whole negation it has been applied, so it is logical equivalent to for all x, sum of x will become all of x, then double negation of p of x, then logical equivalent to for all x p of x. Understood? Okay, so using these we are going to simplify some of the formulas. We'll see and we are going to solve some of the problems. We'll see those things. Okay, thank you.